So in the next theorem, we're going to demonstrate that any Cauchy sequence actually converges. So let's state the theorem. Suppose that Sn is a Cauchy sequence then Sn converges. All right, let's try to prove this. So first, let's recall the definition of a Cauchy sequence. I'm going to fix again an epsilon greater than 0. Then there exists capital N and R such that Sn minus Sm is going to be less than epsilon as long as N and M are bigger than a capital N. Okay, so with this in mind, let's actually rewrite the same expression without using the absolute value sign. So this would be equivalent to saying that minus epsilon is less than Sn minus Sm less than epsilon, again, if both M and N are less than capital N. And I'm going to add Sm to all three sides. So the equivalent statement to this one is that Sm minus epsilon is less than Sn less than Sm plus epsilon. Again, if both N and M are greater than capital N. So what can we conclude from this? We conclude that if we fix M equal to, let's say, N plus 1, so that M is bigger than capital N, and we have that Sn plus 1 minus epsilon is less than Sn less than Sn plus 1, right? Because M again is N plus 1 plus epsilon. Now, because I fixed M, then I allow only N to vary. So this should be true for all N that are greater than capital N. Okay, so if this is so, then I can conclude next the following thing. I'm going to choose any k that is bigger than capital N. If I take any k bigger than capital N, what I will have is that Sn plus 1 minus epsilon less than Sn less than Sn plus 1 plus epsilon. So I chose k bigger than capital N. So if I now take n bigger than k, in fact bigger or equal than k, then if n is bigger or equal than k is bigger than n is bigger than capital N, and so then the statement that I have over here still applies, right? Because at the end of the day, n is bigger than k. But that means that Sn plus 1 plus epsilon is an upper bound on the set that consists of all Sn with n greater or equal to k. And because Sn is greater than S capital N plus 1 minus epsilon for any n again, then we also have that Sn, so end, Sn plus 1 minus epsilon is a lower bound on the same set, Sn, n greater or equal than k. All right. So if then that is true, the next thing that follows is that S capital N plus 1 plus epsilon is an upper bound on this set. Supremum of the same set is its least upper bound. So therefore Sn plus 1 plus epsilon is going to be Sn plus 1 plus epsilon is going to be greater or equal than supremum. Supremum n bigger or equal than k of Sn. And also Sn plus 1 minus epsilon is a lower bound on the same set. So then the greatest lower bound for an infimum is going to be less or equal than an infimum. So and the infimum and greater or equal than k of Sn should be greater or equal than Sn plus 1 minus epsilon. But also another thing that I know is that the supremum over some set is always going to be greater or equal than the infimum over the same set. So I can just get rid of and say that this is greater or equal than the infimum. Okay? And so then, in addition to this, what else do we know? We know that also lim sup. Actually, let me do something different here. Remember that we denoted this number by Vk and this number by Uk. And we found out that if we take a limit as k goes to infinity of Vk, we got lim sup n goes to infinity of Sn. And if we took a limit k goes to infinity of Uk, that was lim inf n goes to infinity of Sn. So if I take this inequality, set of inequalities that I proved here, these inequalities are valid for every k which is bigger than capital N, right? So let's re-emphasize this here. For any k bigger than capital N, because my choice of k was just that it must be bigger than capital N. And so then if I take a limit of the sequence, sequence vk is always greater or equal than a sequence uk. So if I take a limit of vk, it should end up being bigger or equal than the limit of uk, as we discussed during the last lecture, last couple of lectures ago. So because this sequence is bigger than this sequence, the limit of this is bigger or equal than the limit of that. And likewise, the limit of the sequence, because every element is greater or equal than s capital N plus 1 minus epsilon, and here every element of vk is less or equal than Sn plus 1 plus epsilon, then the limit, the same set of inequalities should hold. So then, sending k to infinity, we find that S capital N plus 1 plus epsilon, this is greater or equal than lim sup as n goes to infinity of Sn, right? That's the limit of Vk as k goes to infinity. This is greater or equal than lim nth as n goes to infinity of Sn, and that number is always greater or equal than Sn plus 1 minus epsilon. All right, so that's what we have. All right, so what can we do with this? We're going to only consider a part of this inequality. In particular, I'm going to just be concerned with this part. So remember that I got this inequality by fixing little m, so a long time ago here. At some point we fixed m to be capital N plus 1, and that led us to this inequality. And the only reason why I chose capital N plus 1 was that made m larger than capital M. Well, but if I make m equal to capital N plus 2, same thing should work. If I make it capital N plus 3, same set of inequalities can be established again. So now letting m to be equal to n plus 2, n plus 3, etc. We obtain that the same inequality, same actually chain of inequalities, that this thing is valid for any m instead of m plus 1, for any m which is bigger than capital N. All right. Okay, so like I said, I want to examine now this identity, this inequality. So from this inequality, it will follow that Sm is going to be greater or equal than lim sup n goes to infinity of Sn minus epsilon, right? If I subtract epsilon from both sides. And this, again, should be true for any m that is greater than capital N. Now, if this is true for any m greater than capital N, then if k is bigger than capital N and m is greater or equal than k, so k is bigger than capital N, m greater or equal than k means that m is bigger than n, so then the same inequality will hold. We have that Sm is greater or equal than lim sup n goes to infinity of Sn minus epsilon, right? That is going to be true. And therefore, lim sup as n goes to infinity of Sn minus epsilon, this guy is an upper bound, or actually a lower bound, on the set of Sm with m greater or equal than k, right? Because for each Sm greater or equal than k, for each m greater or equal than k, Sm is going to exceed this number, and that's a number, right? Because epsilon is fixed, and lim sup of my sequence is a number. So this thing is a lower bound on that set, and if it is a lower bound, then the infimum of the set must be greater or equal, as the greatest lower bound must be greater or equal to that lower bound, and so if I take limit, well, no, hold on. If I take the, what was I going to do here? Yeah. If I take the infimum when n is greater or equal than k, actually not n, but m, because my index is m now, m is greater or equal than k of Sm, that's the greatest lower bound on Sm when m is greater or equal than k, this should be greater or equal than lim sup n goes to infinity minus epsilon. And this should be true for any k bigger than n, right? Because again, my choice of k was simply defined by the fact that it's bigger than n. So I can choose other k's and exactly the same thing will follow. So this is true for any k bigger than n, capital N. All right, and this number again, infimum of my sequence starting from a certain value of the index from k, that was denoted by uk once again. And what do I know about uk? I know that uk in the limit goes to lim inf n goes to infinity of Sn, right? And so if this guy goes to lim inf, and if every term of my sequence in terms of k, every term, every uk is greater or equal than this fixed number, then the limit must be still greater or equal than that number. So this is still greater or equal than lem sup n goes to infinity of Sn that I lost here minus epsilon. Okay, so this happens when k goes to infinity. So then what can I conclude from that? So I know that this must be true. What did I do in the beginning with epsilon? Just pick the random epsilon greater than 0. So that means that this conclusion that I just made, this should be valid for any epsilon greater than 0. So this is a number, this is a number, this is a number, right? What can I do with epsilon? I can let epsilon to be as small as I wish, which means that I can let epsilon go to 0. So letting epsilon go to 0, what I get is the same expression, but now without epsilon. Right? So what we do, we establish a fact for some non-zero epsilon, for epsilon slightly larger than 0. Then the end result ends up being independent of any index, right? Because again, this is just a number, this is another number, so a number is greater or equal than another number minus an arbitrary positive constant. So that means that arbitrary positive constant can be taken as small as I wish, can be sent to 0, and so without epsilon, the same conclusion is going to hold. But also, somewhere above here, also we have that, in fact, always, and we proved that before, lem sup is greater or equal than lem nth. So then, since always lem sup as n goes to infinity of Sn is greater or equal than lem nth, n goes to infinity of Sn, what we get is that these two guys are greater or equal than each other, and then also less or equal than each other. And that means that the only possible choice is that they're actually equal to each other. So therefore, lem sup n goes to infinity of Sn must be the same as lem nth, n goes to infinity of Sn. And then using a theorem from last time that if lem sup is equal to lem nth, that means that the window of oscillations at infinity of your sequence is going to collapse to a single point. So that means that the limit of a sequence exists, right? So that's by the theorem from the last time. So therefore, limit n goes to infinity of Sn exists, and it's actually equal to both of these limits. But I don't care what it's equal to. What is important for me is that the limit exists, so the sequence converges. So we proved this theorem, and therefore, if we combine the results that we have just established, we have the following theorem. Any sequence of real numbers converges if and only if it is Cauchy. right? If a sequence is Cauchy, it converges. So that's a theorem that we just proved. And slightly earlier, we proved the opposite fact, that if a theorem converges, then it must be Cauchy. Somewhere when I proved this last theorem, I used the fact that the sequence of real numbers, not a sequence, any set, bounded set of real numbers is going to have a supremum. Right? That is something that I use, for example, here, right? I have a bounded sequence of real numbers bounded by, let's say, this. Then I claim that the supremum of the sequence exists and is less or equal than the number. So we're using a completeness axiom, so that means that most likely this inverse result that we just proved, that if a sequence is Cauchy, then it converges, that only should be valid for the spaces where, completeness axiom holds. So for real numbers, completeness axiom holds, so obviously then this result is going to be true. But if you recall, for the set of rational numbers, this was not true. That completeness axiom was not valid because the proposed supremum of a sequence might end up being an irrational number which does not belong to rationals. So in that case, then the limit of a Cauchy sequence might not be rational, and so in that case, a Cauchy sequence is not going to be convergent in a set of rationals. Let's try to do an example of that. So let's suppose that, let's see, so suppose that Sn, and let's make this an example. E is equal to 0.1, 2, 3, etc., all the way up to n. All right, so then what do I know? Then Sn, each Sn is a terminating decimal. So this sequence is a subset of the set of all rational numbers. All right, so it is a subset of all rational numbers, and also, and of course, one other thing is because it's a subset of rationals, it's also a subset of reals, right? Because rationals are a subset of reals. Okay, so then if I look at this sequence in a set of all reals, what I would see, so in R, this sequence is going to converge. So it converges to what? It converges to 0.123 and so on. So it's going to be now an infinite decimal, which is neither terminating nor repeating, right? So a non-repeating decimal. And so therefore, Sn converges to an irrational in a set of all reals. All right, but then if it converges in a set of all reals, then the same sequence, Sn, must be a Cauchy sequence. That is just a consequence of a theorem that we proved a moment ago, right? Any convergent sequence is going to be Cauchy. All right, so if it is a Cauchy sequence, then if I look at it from a point of view of a set of all rationals, then it is still a Cauchy sequence, right? Because Cauchy sequence simply says that the distance between Sn and Sm is going to decrease as I move n and m to infinity. So if a sequence is a Cauchy sequence among all rationals, it also is a Cauchy sequence. If it is a Cauchy sequence in reals, it must also be a Cauchy sequence in rationals, right? So Sn is Cauchy sequence in R, and therefore Sn is also a Cauchy sequence in Q. So, however, the limit of Sn is, we just said, it's irrational. So it's not in Q. So, in a set of all rational numbers, then our result is not valid because I found an example of a Cauchy sequence in Q which does not have a limit in Q. So if we just live in Q, then a Cauchy sequence and a convergent sequence mean two different things. Convergent sequence must be Cauchy, but Cauchy sequence does not have to be convergent in Q. So therefore, Cauchy sequences in Q do not have to be convergent in Q. All right, and so next time we're going to apply these theorems that we established today to some new situations.